All right, here we go. Next chapter, two proportions. We're going to start with the inference. And today we are just going to do two proportion Z tests, not intervals. We'll do intervals tomorrow. So we will here it says that you're going to be able to demonstrate the two proportion Z interval. That will be tomorrow, but definitely we will learn how to do phantoms, run a significance test with two proportions. So if you go on over to page 35, I just kind of lay the groundwork for this. And so what you're going to find is that in real world, running a test with two proportions or running a test with two means is actually much more common than one proportion or one test or one mean. Because think of any experiment. When you have an experiment, what do you do at the end of the experiment? You repeat with the other subjects, but what's the last thing of our strap me capped? What's our CAP at the end of our strap me capped? We compare the average or the proportions. So we compare the proportion in one group, treatment group, to the proportion in the other, comparing two proportions. Maybe the proportion in people who have relief with medicine A and the proportion of people who have relief with medicine B. Compare the two proportions to each other, that kind of thing. So that is when you run a significance test with two proportions. Okay, now here's where we're headed with this tomorrow, FYI. Let's say I go run a test and I go, ooh, this medicine is so much better than the old one. What if I say the new medicine is so much better than the old, but then I want to know, well, how much better is it? How much better is it? I want to estimate a number. I want to estimate how much better it is. What do we know how to do in statistics that estimates a number? What can we do to come up with an estimate of a number? Estimate a number. What do we know? We want to be a certain percent confident that we contain that estimate, or that we actually captured the true proportion of blah, blah, blah. What is that? Yeah, an interval is going to estimate that number. So if we say, woohoo, yay, the medicine B is significantly better. Well, how much better is it really? We're going to make an interval to see how much better it is. Okay, and so we'll talk about that tomorrow. But let's go ahead and talk about running our significance test and interval. But we have, guess what? Our assumptions and conditions. Woohoo! Not only with one group, but now with two. Dun, dun, dun. Okay, so we have our assumptions and conditions with two groups. So let's talk about it. You're going to get real twice. You're going to get real twice over. Actually, we are going to just do it in one fell swoop. It won't be quite as much as having to get real two separate times. You put it all together. Let's see. We will say that the subjects in both of the groups are either randomly selected, or if it's an experiment, say we have experiment, can you just randomly select from the population and then force them to do a certain treatment? Can you randomly select people and then force them to do a treatment? No, we can't force them to just they are going to pretty much be what? Volunteers. Good. So we're pretty much going to have volunteers. Where does randomization then come in an experiment? Not with what? Deciding which what? Deciding which treatment, see which treatment they get assigned to. Okay, so in an experiment, which is what a lot of these studies are going to be, that we're going to have to make sure we say randomly assign them to the treatment group. So make sure when we do this, we are addressing if these subjects were randomly selected, or if it's an experiment, we are randomly assigning them. Okay, that's important. And I say that because a few years back, people lost credit on their conditions if they didn't specifically say we're randomly assigning them to the treatment. Okay, and then here is our independent piece. We'll come back to that in a second. Down here, successes and failures. What is that? To have at least 10 successes and at least 10 failures. That's our large enough, but we have to make sure we do it for both groups, saying we had at least 10 successes and failures in this group and at least 10 successes and this failures in this group. Okay, but let's talk independence. This one's, we've done that one before, our 10% condition. What is, explain to me, is that a less than or a greater than, and what is the purpose, and what is it doing, and what's going on there with the 10% thing? It's a less than, and why am I saying something such as 143 is less than 10% of all the population 1? Why do I care that it's why do I care it's a small sample compared to the population? Because what? Ding, 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 ding. It's a small enough sample out of the population that it's not going to what? Change the probabilities. Okay, so remember our little cup of M&Ms? That's like so insignificant compared to all the M&Ms. It's not changing the proportion of your blues that you get in your cup. Okay. All right. So now, hey, here's the number one mistake I keep getting, and it just makes me mad. I see people doing this, and I'm just going to go. I need to go talk to your elementary teacher. Because if you think that on the number line 143 is less than 0.10, then we need to have a talk, okay? 143 is not smaller than 0.10. What's missing here? Yes, 143 is less than 10% of all of whatever population subjects it's talking about. Okay, so please quit just saying less than 10%. Okay, all right, here comes, so this says identify the differences in the 2 sample assumptions versus the 1 sample assumptions, and here it is. This statement right here, here is the difference. If I've got people in medicine A group and I've got people in medicine B group, what is important about those people? No. What's important about the people in medicine A group as compared to the people in medicine B group? They're what? They aren't the same. In fact, I need to make sure that they are different. I need to make sure the people that take medicine A are not also in the taking medicine B. I mean, how's that work? Yeah, so they have to be, the groups have to be independent of each other. Here's an example. Here's another example. I used to be doing a lab in here, wrong, for years. And one time I went, after I kind of understood this, I went, I think I'm doing that lab all wrong. Do you remember when we did our blue M&Ms lab where we were getting the proportion of our blue M&Ms? I used to have us also get the proportion of orange M&Ms out of our same cup. So I'd say, while you're got your cup of M&Ms, get the proportion of blue and the proportion of orange out of your one little sample. So one year I said, hey, look at all these proportion of blue M&Ms. They're kind of high. And then I went, let's look at our proportion of orange M&Ms. They're kind of what? If your proportion of blues were kind of running on the high side, what do you think was going on with the oranges? They were smaller because they came from the same cup. So see, they were kind of related. And so that was a bad thing. So your samples have to be independent of each other. If I had done one separate cup and another separate cup, that'd have been a different story. All right, so that's the big deal. That's get real with, I, not just one eye, 2 eyes. Okay, next thing, RIIL. Here is let's talk about the null hypothesis. This is interesting. So now we're going to say, hey, nothing special. The medicine A has the same proportion of successes as medicine B. That's our null hypothesis, unless you show me it's significantly better. But I want you to think about this. These are algebraically the same thing. I typically write what the top one says, but sometimes people write this bottom one, and I just don't want you to be thrown off if you see this bottom one, because it means the same thing. Let's think about it. What does this top one say? That the proportions are what? Good. Proportions are equal, which it says right in the sentence above it. What does this one say? There is zero what? Yeah, there is zero difference between the proportions. Do those things mean the same thing? Yeah. Zero difference between two things is synonymous to saying they are equal. Okay. So those are equivalent, and I just want you to be aware of that notation. All right, next. Here, let's discuss HA. Of course, here's the way that I'll pretty much write them. Either one proportion is less than, greater than, or not equal to the other, which would correspond to the difference being less than 0, greater than 0, or not equal to 0. Okay, there it is. So that is the foundation of our two proportion tests. Now, let's look at the next page, and it is a written out example by me. Oh, wait, sorry, not the next page. The next page is something we're going to do tomorrow on intervals. The page after that ties them together, intervals and tests. And then it's page 38. There we go. Page 38 is a phantoms with all of Miss McClellan's stuff written out. So let's just kind of quickly look at it, and then we'll go do one of our own. So here we go. All right, a two proportion z-test. First thing, parameter. Define your parameter. But how many parameters do we have since we have two separate groups? Two. So you have to define both of them. You're going to want to say that make the P1, you're going to make that about the proportion for population 1. And then the second one is going to be about population 2. You know, for example, the proportion of people who experience relief on medicine A, the proportion of people who experience relief on medicine B. Those are your two different populations. Okay. All right. Then H in a phantoms is your hypotheses statements. So the null, of course, is that they are equal, and the alternative is that less than, greater than, or not equal to. Okay? All right. Now, here's how the conditions might look. I'm going to just demonstrate. First condition is going to be, or assumption, assuming this is right, or saying we're assuming these need to happen, random. And that we're saying that you have to state both groups are randomly selected, or if it's an experiment and you have treatment groups, then you don't say randomly selected, you say randomly assigned. Okay. So put that in there because I didn't have it written there. Randomly assigned if it's an experiment. All right. Now, independent. So we have to show in one, and you know why I have adults written there? I don't know. It should say this first sample is less than 10% of all population 1, and the second sample size is less than 10% of all population 2. So cross out the word adults. I don't know why I have that there. And what's the new independent rule? These two samples have to be what? Independent from each other. Nobody is in both groups. The two groups have to be independent of each other. That's the extra special I. We're so extra special. I am so extra special. Okay, so that's our extra special I. Okay, and then large enough. Notice large enough has to happen for both groups. So we'll have large enough for group 1 and large enough for group 2. So here is our 10 successes and 10 failures for group 1. And here is your 10 successes and 10 failures for group 2. And then don't forget to conclude, approximately normal model applies. All right. Okay, now, if what we had been doing were one proportion z test and one proportion z interval, what's going on now? We got two proportion z test. And I'm going to teach you how to use your calculator for this. So you want to get your calculator out if you haven't gotten it out so far. Okay, because when we do one problem in a minute, we'll use our calculator. And then O, obtain the p-value and compare to alpha. What's after O in phantoms? Our M, which is make a decision, and then your conclusion and state your conclusion, all the same. So all the rest is the same. Okay, you guys, one thing I want you to know is that for the whole rest of this semester, you're going to find we say, oh, look, this is just like before with here's a little difference. Oh, look, this is just like before, but just this little difference. So getting the understanding of what tests and intervals do, now we just build on that, okay? So we have a huge chunk of understanding underway already, and we just now tweak it a little. Okay, so the next page is a interval that we'll do tomorrow, so skip that. And let's go to this page, which is, I don't know what page. What's this one? 40? Okay, page 40. So what I would like for you to do is take a look at this page 40. I want you to read it. And what we're going to be doing is talking about our volunteers who were we have volunteers, and they get randomly assigned to two different treatment groups, okay? So I'm going to give you a moment to read so that you understand what this problem is about. And I want you to think to yourself, I want you to think in your brain, what are the qualities of the two different treatments? Okay, what are the two treatments? All right, take a few moments for that. All right, so what are the treatments for group 1? Good. So group 1, these are all smokers, by the way. Okay, so these are all smokers who volunteered. And so our group 1, they have a nicotine patch, but they also go to counseling, a support group. And then group 2 is the patch only, the nicotine patch only. So you remember treatments, state your treatments very well. What do we do after treatment? State your treatments very well. Then we do what? Measure each subject's response to them. So what would we be measuring in this problem? Yeah, the proportion who do what? Okay, the proportion of each group who quit smoking. This is kind of just a quick outline so we have in our brain what's going on. Measure each subject's response to them. Strap me, cat. Strap me, cat. Shake your bag up. And then at the end, after we have collected our two proportions, what do? Compare the average or the proportions, in this case proportions, to see which treatment or if there is a significant difference in the treatments. See, when we learned that experimental design at the beginning of the year, it was all leading to what we're doing now so that we can see if one is significantly different produces significantly different results than the other. Okay, let's move on to the next page, which is where we're going to put all of this, do a phantoms. And so, hold on a second, there we go. So here we go, up at the top. So we're going to define what's happening first, and we've got this proportion. Okay, what would P1 be? Proportion of what? Think about it. Think in your brain without saying out loud. Okay, so what do you think P1 is? Proportion of, and what's our denominator? What's the group? All smokers who wear the patch and go to counseling. So that's the denominator. The proportion of all. And you know what? I put such in there. You know why I put such? Because are we really going to be able to generalize to all smokers in the whole wherever? Because what did these people do? I mean, they were volunteers. And so really, do you think volunteers might have a different quality than just all smokers in general? Yeah, they might already be motivated in some regard to quit. Okay, so that's why it's all such smokers, all these kinds who wear the patch and go to counseling, who quit smoking. That's your numerator. Out of all such smokers who wear patch and go to counseling, the proportion who quit. Okay. So then what would be our second proportion? Proportion of all such smokers who wear the patch only, who quit smoking. All right. Okay. Now let's do H, our hypothesis statements. So what would the null hypothesis be? Good. Same success rate. Nothing special. P1 equals P2. Okay, good. All right, what would HA be? Yeah, we were wondering if the counseling group made a significant impact, significantly higher rate of success than just patch only. Okay. All right. Very good. Okay. So here we go. Now we've got some conditions and stuff. So let's do our random one, a random. So what should we say about this? Were our subjects randomly selected from all people or all smokers? Were they randomly selected from all smokers? No, they were not. They were volunteers. So random selection is not what's going on here. What's going on here? Random assignment to the treatment groups. So we have a situation where it did state in the problem that the subjects are randomly assigned to both treatment groups. Okay? That right there just made the difference between you getting credit for all the assumptions or not. And that's annoying. But I'm just telling you, I don't make the rules. I'm just telling you how to play. But it is important. Okay. Independent. So what's our typical component of independence that we manage? What do we typically handle? the 10%. The 10%. So we got to do it for both. So one of them says this, the 143 is less than 10% of my first group, which was the patch and counseling smokers. So 143 is less than 10% of all patch and counseling smokers. And 151 is less than 10% of all patch-only smokers. Okay. Now, while you're writing that, I'm going to tell you a common mistake. Common mistake. People want to add them together and say 196 is less than 10% of all smokers in general. You cannot combine it together and say 196 is less than 10% of all smokers. Okay. These are two different populations. Okay. All right. What was our extra special independent component we added today? That these subjects are independent of each other. I do not have somebody in that I'm counting. I'm not double counting somebody in both of the groups. So the subjects in groups 1 and 2 are independent of each other. Subjects in groups 1 and 2 are independent of each other. Okay. Okay, now what's next? Getting real. What's left? Large enough. Okay. So let's go look at the previous page and let's find it. Okay, so we can see, because we have to do at least 10 successes and at least 10 failures for each group. So let's look here. After 6 months, 46 of the 143 smokers in group 1 quit smoking. That's our first numbers. So how many successes are there? 46. How many failures are there? 97, the other part. Okay, so here's how that looks on this. Here we go. Look. Oopsie, that didn't help. See that right there? Here's my first group. And I didn't label it, but I think it's okay because you kind of have been defining your numbers all along, so it's okay. 46 is greater than or equal to 10. That's the 10 successes, which meant that the other part of the sample, the 97, is greater than or equal to 10. Okay, so there was that part. Now, okay, go find the information on the other page about group 2. Group 2 says 30 of 151 smokers in group 2 were successful. So here I go. There it is. Successes, 30 is greater than or equal to 10, and then failures would be the 121. It's greater than or equal to 10. And then we'll finish it off with approximately normal model applies. Approximately normal model applies. Okay, we're working our way. Now we're to the name of the test. And what is the name of this? It's a 2 proportion z-test. Okay. So now I'm going to teach you how to do stuff in your calculator. We're going to do a 2 proportion z-test in our calculator because T means test statistic. That means get your z-score. Okay, so everybody to your calculator. Here we go. Okie dokie. We're going to go to Stat, and look at the tabs at the top. It's got Edit, Calculate, and Tests. Where do you think we're going? Tests. So arrow over to Tests. And there's a whole host of menu items. We're interested in the proportion tests. So what do you see there? I think number 6, a 2 proportion z-test. Now, FYI, what do you see number 5 is? A 1 proportion z-test. And what do you know about a 1 proportion z-test? We just already did that, and we did them by hand. Okay, so just so you don't get your hopes up too high, you are going to have to do the 1 proportion z-test by hand always still. No calculator shortcuts for you because the 1 proportion ones are simple. And I know from experience that if I do not keep you doing at least those simple ones by hand, you lose process of the fact that you're getting a z-score and then your norm CDFing so that you get your p-value and so on and so forth. Now, here is why I let us do the calculator for the 2 proportion ones. Let's just examine the 2 proportion standard deviation on the formula chart. Here it is. There's a whole heck of a lot of mistakes we could make in here computationally. So I'm going to try and minimize that by letting our calculator do it. But let's study it because there are multiple choice questions where we have to be able to kind of like follow what the heck's going on here. So let's study it. What do you see right here in this first circle? It's P1 times 1 minus P1 over N1. What's that? We've done that before for standard deviation, but that one's for sample 1. What do you notice in this second circle? It's the same, but for sample 2. Okay, and then we square root it. But now, FYI, why are we adding? Why does this variability get bigger? You always have to add with the standard deviation things because remember, if I have cereal and I don't know what's in the box and then I pour out some in the bowl, I'm not sure how much I poured out. I'm even more unsure, more variability in what's left. So it's always adding. Okay, so see, there's the formula. Hence, it's got a lot of problems there. So we're going to let the calculator minimize those problems for us. So here we go. All right, don't put these numbers in. These are from a different problem. Okay, but so X1 and N1, that's your data for sample 1. X1 is the number of successes. How many successes did our first group have? It had 46. Okay, good. All right, N1 is not the failures. N1 is what? The whole sample size of sample 1. And what size was that? 143. Okay, good. X2 is the number of successes in second group, which was 30. And how many were in that one sample? 151. Now, take a look at the next line. That's where you're wondering if P1 is not equal to, less than, or greater than P2. What were we wondering in this case? We were wondering if the counseling gave us a higher success rate than the patch alone. Okay, now go calculate. Voila. There's information, and so let me show you what all that is. Okay, and talk to you about it. So here is I've got a picture of calculator stuff going on here. Okay, so let's take a look at it. There, of course, is your z-score. Yay, there's your z-score. Okay, and then so there's our z-score. That's our test statistic. Okay, you see the p-hat 1? P-hat 1 is what the proportion is for the sample proportion, 46 out of 143. Okay, so p-hat 1 was that 46 out of 143, and p-hat 2 was the second group's 30 out of 151. Okay, so that's just p-hat results. This p-hat with no subscript, that's combined. That's like adding, that's like 76 out of 196. So they kind of like just lumped them together into the total success out of total in the sample. So let me show you again. That came from 76 out of 196, which we're not really interested in that. Okay, so what is this right here? I like to think it's population P, but it's not. It's not a capital P. It's actually, and it's the p-value. So that's one fallacy of the calculator, is that this is the p-value, not the population p. So if I took this z-score and norm CDF'd it from 2.41 to 99, that's how I would get my p-value of 0.008. Okay? In fact, if I went and did that real quick, look here. Let me norm CDF for my z-score. Oh, I just cleared that out. That's all right. To 99, voila. There's the p-value, 0.00802, whatever. Okay. So that's what's happening. The calculator is doing it for you. And so there's your test statistic. What's the next thing? O is the obtain a p-value. And there it was, compare to alpha. And now we want to make a decision. If that p-value is low, what are you going to do? Okay, we're going to reject HO. It's a recording after all, you know. Okay, we don't need evidence. Okay, but anyway, if I reject HO, so since 0.008 is less than 0.05, I reject HO. Now, what do I say? There is evidence of HA, but I got to do it in context. There is evidence. What is HA saying? HA says P1, the proportion of smokers who wear patch and counseling who quit smoking is greater than P2, which is the proportion of smokers who wear patch only who quit smoking. So here is what that looks like. There it is. I have evidence that the proportion of smokers who wear patch and go to counseling quit more frequently than the proportion of smokers using patch only. Okay? So I want to do two things. I want to tell you what your homework is, and also then show you one other little calculator problem that you might face. So I want to kind of have you experience that so that you don't have that problem when you do your assignment. All right. So if you take a look at, if you skip over to page 43, you will see the assignment. Okay. And on this assignment, you're going to only do the phantoms pieces. It has a phantom and a panic, and then another phantom and a panic. So you're going to do problem 1 about Jenny O chicken and store brand chicken, and just do the phantoms, which is on page 44. Okay, is the template. And then problem 2, this is going to be interesting, is about the proportion of women who think men are intelligent and the proportion of men who think men are intelligent. Okay, so that's a good one. And you're going to do that test and put that on page 46. Okay, so there's a phantoms and a panic, but you just do the 2 phantoms. All right, now I want us real quickly to examine this problem, and I want us to experience a calculator error so we know what to do. So this is a problem about Jenny O store brand Jenny O's chicken and the proportion who get contaminated, and the store brand chicken and the proportion who get contaminated. And the problem says 33% of the 75 Jenny O ones get contaminated and 45% of the store brand. You want to know if that's just sampling variability, or if is a store, should you buy the name brand so you get contaminated less? Let's go to our calculator. Okay, let's just practice the calculator part. Stat over to test. Number 6. So here, if I put in 0.33, that is not a number of items. What is that? That's a proportion. So how many items got contaminated? 33% of 75. Enter. And then N1 is 75, of course. Okay. Second group, how many got contaminated? 45% of 75. And then that was 75. Now, what were we wondering? We wanted to know if Jenny O had what in relationship to store brand. We wanted to know if Jenny O had less contamination. So that's a less than. Now, when you go do this, boom, dun, dun, what just happened? You had an error. So let's go quit, go back over there, and let's talk about it. Can you have 24.75 packages of chicken? No, you cannot. The contamination isn't in 24.75 packages of chicken. It's in how many? 25. So this needs to round appropriately. 25 out of the 75 were contaminated. And then the other one, 34 out of the 75 were contaminated. That's how you get it. Because do you know what happened? FYI, what 25 out of 75 is 33? It was 33.3 repeating percent. That's why they rounded it to 33%. And 34 out of 75 is 45 point something percent, and they rounded it to 45%. So see, they rounded the percents when they made the problem. There was a whole number amount of contamination. All right? So that's the calculator problem you might experience that I wanted to warn you about. Okay? Make sure that it is whole number and not percent items. All right, that's it for your assignment there. Yes.